All right, thanks for joining everyone, and welcome to today's APAC seminar. Today we have Matthias Fresacher from Western Sydney Uni talking about diagram monoids. So I will hand it over to him.
Thank you, London. So just a little bit about myself. So I'm a PhD student here at Western Sydney University. I'm going to tell you what diagram monoids are all about. And the other hat that I do have, I'm also the president of the Association of Australian Mathematics Students, AMS, which hopefully you know about as you are here at one of our seminars. But if you don't, then this is probably a good opportunity for you to check out what AMS is all about. You can find our website and go from there. Now, in terms of this talk, I'm happy for you to interrupt and ask questions along the way. Just note that whilst I can see the chat, I may not be able to pay too much attention to it. So it is probably best if you just butt in when you have a question. So let's begin. So first up, we're going to need to know about a semigroup. So a semigroup, we have some set S, and we have a multiplication operation. So this is just a binary operation where we take two elements in our set and we map this to some other element in our set. And for this, we need, for it to be a semigroup, we need this operation to be associative. So that means if I take an A, I'll multiply this by B, multiply BC, then multiply this by A. We want this to be the same as if I did A, B first, and then C, and this is for all A, B, C in S. So essentially we're saying brackets don't matter. We don't have to worry about the order that we do our operations in. So some easy examples that you would be familiar with, say, would be natural numbers and multiplication. That's a good example. An example, a non-example, might be the natural numbers, but say subtraction, because, so this is not an example, because if we have a look at, say, 1 minus 2 minus 1, well, if we calculate that, you get minus 2. This is not the same as if we change the order of the brackets. If we calculate this, we get 0. Obviously, minus 2 is not equal to 0. So this is a semigroup, but we're interested in monoids. So how do we get to monoids? Well, we need an identity. So I'm going to denote the identities as ID, and this is going to be some element in our set, such that if I take any element A and I multiply it on either set, either side of our identity element, we've got to get back our original element. So as you expect, it does nothing. So this is for all A in our set. So if we sort of were to turn, say, our natural numbers into a monoid, we would have natural numbers still, multiplication. What would be our identity? Or just the number 1. Obviously, anything multiplied by 1 on either side just gets us back our original number. Okay, so that is the basic properties of what we're working with. So we are going to be talking about first up the partition monoid. So for this, we sort of have a number of different, I guess you can call them flavors. And this is for a particular choice of n in the natural numbers. Now, we're just going to pick n greater than 1 so we don't have sort of too much triviality. And this n, this is going to be what's called the degree of our monoid. So our partition monoid, this is going to be Pn for that choice of n. We need to define what are the elements in this set. So let's suppose we're going to pick n is equal to 4. That means I'm going to have 4 vertices in a row. I'm going to copy them underneath, and then I can put in edges in whichever possible way I want. So this might be an example of an element in our partition monoid. So I can just draw edges in whichever way I want, and essentially we think of this as being the diagram. So this is sort of where the name comes from. And we care about what are the connected components, so which bits are connected up. So this is obviously connected to here, connected to here. And these are not necessarily unique, because if I say draw an extra edge in here, it's a different graph, different picture, but what is connected to what is still the same. So sort of by convention, we just draw the least number of edges that we keep things nice and clean. Okay, those are the elements. So now we need our multiplication operation. So for this, I'm actually going to draw just a second diagram directly underneath. Say this one looks like this. And then how do I calculate the product of this? So again, it's going to be a diagram. So we're going to have 4 vertices in 2 rows. And to calculate it, I'm going to draw in some vertical in-between edges in between our 2 diagrams. And then I'm basically sort of going to forget about the fact that I have some vertices sitting in the middle here. So let's just sort of forget about these. And then let's see what have we got left, like what is connected to what. So this is still connected to that third one, and this gets connected here through the red edge, gets connected across to here. This red edge doesn't go anywhere, and it gets connected down. So this also gets connected down to the bottom here. Okay, so that's this bit done. Let's look at the second vertex. That's still connected to the fourth one. We go here, down through the red to the second one. So we have a one straight down, and this is connected across here as well. We've done all these top ones, and these bottom ones are all done. Here we have something that's not connected to anything, so that's just going to stay as is. So essentially, we're just chasing through what we have in our sort of reduced diagram. So this would be the concatenation process. Now these are monoids, so we need to have an identity. And the identity for these monoids is going to be, so if we stay with rank 4, it's just going to be all vertical edges. And we can see, well, if we sort of were to concatenate, this is what this process is called, with the identity diagram, but we're not changing anything because all the connections would be the same as we previously had. One notion that we can talk about is the rank of a particular diagram, and this just counts the number of transversals. So a transversal is an edge that links the top and the bottom. So this would be a transversal 2, 3, 4. So this identity diagram here has got rank 4. If we're looking at this top diagram, we have 1 and we have 2 different transversals, so not part of the same block. So we have a rank 2 diagram here. So any block or sort of edges that are only connected to the top or only the bottom, well, they're called non-transversals. Now we do have one operation, a unary operation that we can also put on these diagrams. In particular, a natural, oops, let me spell correctly today, natural anti-involution. And so this is a star map, and this takes diagrams and it maps it to other diagrams. Specifically, if again we look at our example that we had here, what do we have here? This. So if I take the star of this thing, I'm going to get a diagram again. And all I'm going to do is basically flip the top and the bottom two rows. So we had this one linking to 3, that was in the top, that's going to be the bottom now. We had 2 joined to 4, that's in the bottom. The 3 to 3, well, that's going to be the same. And now from the bottom, number 2 goes up to number 1. So we're just flipping everything. And from that, we can see fairly easily that if I take the double star, or if I were to flip this again, I'm just going to be back to where I started. Very much like if you were dealing with matrices and you do the transpose, you change the order. And there is one last one we'll put down here, which is not very intuitive, but just trust me, it does hold. So if we then also include this star operation in our monoid, so we had our set Pn, we had the concatenation operation, we have our identity. Now if we put in the star as well, then this is actually a regular star semigroup. The definition of which, don't really worry about, it exists. The key though is there's a whole lot more other monoids that we can be exploring here. So this was a partition monoid. There's a few sub-monoids of this that are worth looking at. So one example is the Brouwer monoid. Monoid, so Bn. And in this one, we need all of our blocks to have size 2. So what do we mean by that? So if I again look at an example from degree 4, here block sizes 2 means every vertex must be connected to exactly one other vertex. So I could say have this, because now the block sizes, how many vertices are in each block, in each connected component, is always 2. So this is a Brouwer diagram. And as we can, as if you put in a little bit of thought, you can see that you only get, so if say is n is odd, then the rank is also, is also going to be odd. It has to be the same. And you can sort of see that because everything has to be matched up, it kind of just can't be in any other way. And likewise, if n is, say, even, then all the ranks of our diagrams are also going to be even. All right. A slightly different variety is what's known as the partial Brouwer monoid. So this is PBN, and in here, instead of having block size exactly equal to 2, blocks can be less than or equal to 2. So if we look at an example, I can have my block size of 2, but I could also say have some blocks that are just size 1. They're not connected to anything. Another variety, these are sort of going in a slightly different direction. Instead of putting restrictions on our block sizes, is actually on our sort of edges themselves. And this is the planar partition. So this is, now I'm gonna, oops, this is supposed to be curly P, P, N. And here what we mean by planar is if we look up here, we can see we have an intersection of edges. So we're not allowed to have any intersection of edges. So if we draw our diagram, now if I were to sort of put a box sort of through here, all of our edges need to be inside the box and they're not allowed to cross. So I can have something like, this. Okay, so this would be an example. And the box is small, so we can't say we wouldn't be allowed to do something like this is outside the box, that's not allowed. So it really has to be inside of that box, those vertices. In this, we have, from this, we can sort of combine the idea of the Brouwer monoid and this planar idea. And if we do that, we end up with the, let's see, there's one, two, that's right, the temporally lead monoid. Now, sometimes it's also called the Jones monoid. So TL M is going to be the intersection of, so we both need to be Brouwer and we need to be planar. Curly P. So that means we need to have block size 2 and be planar. So an example of, so if I sort of make this into a non-example, I can say add some more edges here. Those block sizes are too big now. Here for temporally lead, we only can have block size 2, so I might have, say, this. So this would be a temporally lead diagram. And just like we sort of used the Brouwer as a starting point, if we get the Motzkin monoid, where this is MN, where instead of the full Brouwer, we just take the partial Brouwer and we make this be planar, planar P. N. So if we recall, partial was block size 2 or less. So I could say have something like this. This would be an example of a Motzkin. And sort of an interesting thing to note here is our temporally lead and our planar partition. Well, we can already see they're sort of fairly closely related. And in fact, our partition, our planar partitions, they're isomorphic to the temporally lead, but if we use twice as many vertices. So I'm not going to explain why that's the case. That's sort of just an interesting result. And it kind of means that a lot of the results you only need to look at one of them if you're working with them, because you sort of get the other one for free up to the number of vertices. Okay. Now we have some more varieties. As you can see, there are definitely a lot of diagram monoids. Next, we have symmetric inverse. And this is a, so IN, this is a submonoid of our partial Brouwer. And here we have that all non-transversals are singletons. Okay, so we start off with a partial Brouwer. So we could have, say, something like this, and then all non-transversals need to be singleton. So we have a non-transversal block here. This is not a singleton, so we have to remove this edge. Now we get a symmetric inverse. Now I sort of keep picking bad examples, so let me put a crossing in here, because I'm kind of giving the game away. We can now consider all of these without crossings being planar. So these are the names are starting to get a bit long here. Order preserving partial permutations. So this is ON. So this is where we say start off with the symmetric inverse, and we ensure that it is planar. Or alternatively, we can start again with this inverse, this symmetric inverse, and we can use the Motzkin, which already includes planar as well. So this is where, say, this crossing would not be allowed. We only allowed straight things. And if you sort of think about the name order preserving, which I spelled wrong, it sort of makes sense if we think of these, if we give these numbers, 1, 2, 3, so on, where does that go? If we have any crossings, well, that's not going to be order preserving anymore, because this one is now something bigger than this one. And obviously partial, because say this one doesn't get back to anything, and well, permutation, because you're playing with the order of things. And lucky last, we get I'll put it here. Lucky last, this one's the easy one. We also get the symmetric group appearing, where obviously, like, every edge is a transversal edge. So this would be symmetric inverse, but we also need it to be Brouwer. So this is SM, because we obviously want everything to be matched to something else, and we don't want any non-transversals to be singletons, or we don't have any, in fact. So that's quite the mouthful, isn't it? And I said there'd be lots of pictures. So let's put all of that into a giant picture. So at the top, we had our partition monoid. So I'm going to use both boards here. And for this, we said, so let's give ourselves space. 1, 2, 3, 4, 5, 6. And for this, we said, well, it was basically just a free for all. You have this one mix up here, 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 and here. Okay, so we have free for all in the partition monoid. Then underneath this, we have the partial Brouwer monoid. So this is where we've restricted the block size to be 2 or less. So we see here some of these blocks are too big. So in here, 1, 2, 3, 4, 6. So here we're only allowed to have block size of 2 or less. So this would be Brouwer. Now I'm going to put in the, let's put in some boxes here. So this sits underneath. Okay, yep, I'm going to run out of space, but we'll deal with that. Then we have also sort of, instead of going down the block size, we sort of have this planar idea. So sitting off to the side here, we have our planar diagrams. So they're also a subset. Let's see if I can squeeze one in here. 1, 2, 3, 4, 5, 6. I can. So in terms of block size, free for all, but we're not allowed to have any crossings of our edges. So this would be an example. This is an example as well. Then from the partial brow, where the block size is 2 or less, well, we have the brower, where we had the block size being exactly 2 all the time. So this sits over here. So let's squeeze like here. 1, 2, 3, 4, 5, 6. 4, 5, 6. So we're allowed to cross edges, but everything needs to be matched up. And this was a sub-monoid of our partial brower. We also had, from the partial brower, we had our symmetric inverse. Also a sub-monoid sitting in here. So this is where we have things being 1 to 1, but no non-transversals other than singletons. 1, 2, 3, 4, 5, 6. So we can have things like this, but all the non-transversals have to be singletons. And obviously block size 2 or less. So this sits underneath as well. And then out here, we starting to get into the intersections. We had Motzkin. Now Motzkin was both a partial, a planar partition, as well as being a partial brower. So that means 1, 2, 3, 4, 5, 6. So partial brower means block size of 2 or less, and we have to be planar. So we can have something like, say, this. That underneath here and underneath here. All right, that's that layer done. Then we have, sitting over here, we have the symmetric group. So that obviously has to be brower and symmetric inverse. Everything has to be nicely matched up. So let's put 1, 2, 3, 4, 5, 6. So symmetric inverse. Symmetric group, well, basically just some permutation. This was brower and symmetric inverse, were the supersets of that. In here we have our temporally lead. So we know temporally lead was a submonoid of the brower. And we also had to have this planar condition, so it sat underneath the Motzkin. Now, just for drawing purposes, I'm going to leave that edge open. So temporally lead, every block size 2, 5, 6, 6, and everything has to be planar, no crossing. So say something like, let's see, that's too far. And here, and here, and here. So we have this sitting inside here. So this came from Brower. And then it also came from our Motzkin monoids. And then over here we had our order preserving. So order preserving meant we needed to have planar, so we underneath the Motzkin. And because we were dealing with functions, we have the symmetric inverse in there as well. So essentially we look like this, but we're not allowed to have any crossings. So 1, 2, 3, 4, 5, 6. 5, 6. So I can have something say like this. And this came from our Motzkin and our symmetric inverse. And then we are pretty much complete, because all we then have left at the bottom is just the identity diagram, which obviously is just a trivial submonoid. So everything feeds into this. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. All right, there we go. So that is basically the family of diagram monoids. Except put a bit of an asterisk on here. There are other ones. For example, the transformation monoid is a diagram monoid, but it doesn't actually fit too neatly into this diagram. So it's not complete. There are other varieties, but I think you can already see there's a whole lot of them, and they're sort of all nicely interrelated, and well, they're pretty cool. Like I sort of do find it quite amazing that particularly these diagrams, if you think about them, if you multiply them together, that you stay within the rules of your diagram, particularly some of the more involved ones, say like temporally leave, that if you have two diagrams, you multiply them together, and then you chase it through, that you still not introduce any edge crossings. That's pretty interesting for me. Right, time for a quick break. So that sort of is the basics. Now let's go exploring a little bit into some more exotic varieties. Let's get rid of this one. And what we sort of explored here were sort of just your standard partition diagram monoids. We can sort of go into some more specialized, more varieties. So remember we were saying that n was some natural number, our degree. Well, what if sort of in, let's say, and wavy terms, n was equal to infinity? So usually this is, say, denoted by n subscripted natural numbers. And in terms of sort of pictorially, an element of this, well, it would just be, well, we sort of just keep going forever and ever. We would have an endless supply of vertices. That makes perfectly good sense. And we can still put in whatever connections we want. Makes perfectly good sense to consider such a thing. So do all of these, what about all of them, like all these submonoids? Well, let's have a look at, say, the Brouwer variety. And in particular, let's have a look at these two diagrams. So I have this diagram, which is a perfectly good Brouwer diagram. And let's suppose I have this diagram. I have one transversal here, and everything else just gets joined along. Again, that's a perfectly fine Brouwer diagram. Now let's concatenate these two together. So we join our inner edges like we always do, and we keep going, what would this be? Well, let's figure it out. So if you play with these a bit, you sort of know that any non-transversals in the top and in the bottom, they're just going to stay the same because nothing can change. So we're just going to have everything linked up here. Likewise, all of these bottom ones are going to get linked up. And then this vertex, well, this goes here and it starts snaking. But we can see it's not going to be connected to the top or the bottom. It's just going to stay like this. It doesn't go anywhere. But that's no longer a Brouwer diagram. So Brouwer with infinite many vertices, it doesn't exist. That's sad. Only the partial Brouwer exists where we're allowed to have blocks of single blocks of size 1. So sort of all of these may or may not exist. So that sort of is one thing to consider. And you can sort of play, I guess, more games with this if you like. And because we did essentially the natural numbers here. Well, I mean, that's a set, an infinite size set. What about if we say pick the integers instead? That makes sense. Instead of just going off in one direction, we can go off in the other direction too. You can play with that in your own time. There is another direction we can go in. And that is in the twisted version. So basically, all of the monoids that we had, we can twist them. Now I'm just going to go through the zero twisted Brouwer monoid because that's actually the focus of my attention. So zero twisted Brouwer monoid. So yes, there is a 0 here. You can have other versions, but we're not going to cover those. So again, there's even more variety you can go into. And this was a B, N, the 0 because we're 0, and a capital phi here because it's twisted. Why is it a capital phi? You can ask some other time. I don't have time at the moment. So what is this twisting business? Well, if we look at an example of 2 diagrams in our Brouwer monoid, say these 2. When we go to concatenate these 2, draw in our in-between edges, and then we discover that, well, we have a loop in here. Because that's not going to be connected to either the top or the bottom row of vertices. And then in our twisted version, we're not allowed to have loops. So then just straight out by definition, this is just going to equal 0. I'm done. Doesn't equal any other diagram. If I didn't have a loop, we'd have the same concatenation as we did before. And obviously, as you expect, any diagram multiplied by 0 is always just going to be 0. So essentially, we have all the same diagrams that we did before, plus a special 0, and we're slightly modifying the way we multiply our diagrams together. And as I said, this is the 0 twisted version. You can have a D twisted version for basically any natural number. And there is also kind of an infinite twisted version as well, which is even more exotic. I don't quite have time to get into those details. Instead, what we are going to do is we are going to skip ahead a little, and we are going to look at some congruences. So let's make some space. So congruences on, say, some monoid M without multiplication. And essentially, so congruence, usually denoted by sigma, I'm going to use sigma. And it's an equivalence relation. Relation on M. So in some sense, we're identifying diagrams that are in some sense similar or the same, but it has to be compatible with our multiplication. So specifically, if I take two diagrams in alpha and beta, if they are congruent, this is the word, then this implies that alpha multiplied by some gamma is also still going to be congruent to beta multiplied by that gamma. So I can multiply by anything on the right hand side, I'm still going to be congruent. So for all alpha, beta, and gamma in our monoid, which that's not an M. And we actually want this same property to hold on the other side as well. So gamma dot beta. Okay. Now, why do we care about these congruences? I don't quite have time, but they allow us to form quotients. So essentially sort of make our monoids a bit smaller in the same way as normal subgroups are kind of a big deal for people in group theory, or in the same way that ideals are a big deal for people in ring theory. So congruences, that's like the thing that semi-group theorists get excited about. Okay, as is normally the case when we have a definition, what's an example? Well, there's two easy examples. One is the trivial congruence. So trivial means that it is just going to be, so remember it's an equivalence relation, and I'm just going to have it be the set of everything is only congruent to itself. And I mean, that clearly is going to be equivalence relation, that's easy to see. And we can also see that everything is only congruent to itself. That means alpha and beta would have to be the same. So obviously this is going to be the same. Again, we can very easily see this is going to work. And the other easy example is the universal congruence. And this sort of is basically the opposite, where we just make everything be congruent to everything else. Again, we can sort of pretty easily see we're going to get an equivalence relation if we do that. And well, if everything is congruent to everything else, it doesn't matter what we end up with here, it's going to be congruent. And obviously, sort of these are very much the two extremes. We sort of have to be in between these two. In fact, we sort of get a lattice of all the different congruences. So let's put that up. So a congruence lattice. So where we say we always have the universal congruence at the top, we have the trivial congruence at the bottom, and then we would have all sorts of different congruences sitting in here, which are going to be subsets of each other. So, oopsie, wrong direction. So all of these are going to be subsets, and you sort of usually don't want inequality. And as normally is the case in your lattice, we can have, for example, if we have a sigma 1, a sigma 2, and a sigma 3, say, sitting in here. So here we have sigma 1 is the join of sigma 2 and sigma 3. And likewise, we could sort of have the reverse picture where we have a sigma 1 and a sigma 2. And here we have a sigma 3. Here, sigma 3 is going to be the intersection of sigma 1 and 2. And you can check join and intersection would satisfy these conditions. So we get these lattices for each of our monoids. And if I were to take just an arbitrary monoid and I'd ask, what is the congruence lattice? What are all the possible congruence I could have? It's going to be a horrendous mess, like a gazillion different branches in all sorts of directions. Horrible, horrible thing. But something remarkable happens if I say, look at a diagram of it. This is one of the reasons why they're so interesting and useful to study. Because, for example, if we look at, say, the symmetric group, well, its congruence lattice, and this is sort of folklore, is going to be, we have our trivial congruence. So these are just your normal subgroups. So just your identity. Then we have the alternating group. We have the symmetric group, and well, that's already our universal congruence. Obviously, you might have Klein 4 sitting in here when n is equal to 4, but we'll kind of forget about that technicality, or when n is small. So incredibly simple, just a chain. In fact, for IN and for ON, so the what was it, symmetric inverse and order preserving inverses, they're also just chains. So just simply one single chain, no branching off or coming back together like this. So this is from Lieber in 1953. And this is Fernandez from 2001. Then in the partition monoid, this is from East and a few others from 2018. They discovered that we have sort of a chain at the top, and then let me draw this out. So then we have 3 in a row, 1, 2, 3, 4, 1, 2, 3, and 1 in the bottom. So we end up with basically, whoops, it's connection, with these boxes in a sense, box, 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 down, 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 joins up, and then I'm going to put in the back boxes. So we sort of have this long chain, which may depend on the degree, and we have some boxes at the bottom. Now the same group of people, this turned out to be quite the big paper that they wrote. They also looked at the partial Brouwer, and the partial Brouwer, we have to split it off into odd and even degree. In the odd, we just get a chain, and at the bottom we get a single diamond. And in the even case, I'm going to say basically the same as this, plus an extra box. So see how we sort of have one box here, two box, there's a third box there. Okay, then for the Brouwer monoid, they oh dear, did I get my notes wrong here? Yeah, that's partition monoid. Yeah, I'm getting my notes mixed up. So this was, so we'll actually move this over here. So this is actually, yeah, I did not write this out properly. Ah, no, that is correct. My bad, my bad. That was PBN, and then Brouwer is, I'm making a mess of this. Okay, check their paper. They have, you get all of these different lattices. The point I want to make, I'm looking at the time, is we'll finish up with my work. So if you recall, I was interested in the zero twisted Brouwer monoid, and in this one, so this is work I did last year, not from a decade ago, not that old. So in the odd case, we again just have a chain, and in the even case, we get again a chain at the top, and then we get 3 diamonds at the bottom. So that's the brown monoid. And then this year, I looked at the 0 twisted temporally lead. So this is from this year. And here, I, again, for the odd, just a chain, which is becoming a bit of a pattern. But in the even, we almost end up with something like this. We still have
I'm gonna be like so.
and then one sort of extra bit at the bottom. Okay, now if you do one particularly for the Fowler situation, if you want more details on this, I do have a YouTube. So watch my OSMS talk on YouTube. And also, this is the integer sequence A3688923 in the online encyclopedia of integer sequences. So this is for the Brower, you can check that out. And if you're interested in drawing all of these things in, say, a nice LaTeX package, that does exist. I made that. You can look at PM Draw Partition Monoid, yes, fancy name. And I will end that there. Are there any questions about diagram monoids? Or are you so knowledgeable now, I'm going to be out of the job and worried that you're going to publish my thesis before I'll finish?